Today, we are going to learn exactly what neural nets are. Now, neural nets learn on data, so we have to start with some data. They can learn any function, so let's choose a function that's easy but not too easy. We'll just go with x squared, and we'll do a regression task. And this step doesn't matter for the purposes of our exploration today. Now, here's the model. This is a neural net. This is the simplest neural net you can possibly have. It's one layer, and the input is the output, but that doesn't actually do anything. So if you try to build it, my website will give you a little message here. So what is a neural net? It's a series of layers, and each layer operates on the preceding layer. So let's add a layer. Now that message goes away. And this is one of the simplest layers we can have. And we'll go into more detail on exactly what it does. It takes the first layer, which is our input data, and operates on it. Let's go ahead and add one more of these. And let's add one more. And as I mentioned, they all operate on the preceding layer. So this layer gets operated on by this layer, which gets operated on by this layer, which gets operated on by this layer. And then that is our final output of our model. And that gets fed into the loss function, which tells the neural net how it needs to update its weights. Now, I removed the biases just to make this as simple as possible. And let's go ahead and build the model. And let's ignore this warning message for now. So what exactly is this diagram showing us? I drew it out right here. So we have our input layer, and then we have our first dense layer. That layer is simply a parameter, a weight, multiplied against the input. That's all it is. And the next layer is a weight 1, multiplied against the output of the first dense layer. That's all it is. And then again, the last dense layer is simply one parameter multiplied against the output of the previous layer. And that's all these dense layers are. And if you do the math, if you substitute each output, what you get is 3 weights multiplied against our input data. And 3 weights might as well just be 1 weight. 3 numbers multiplied together is just another number. And so all we did is we multiplied our input data by a number. And if you don't believe me, we can go ahead and train this model. Let's go to the parameters. It doesn't really matter too much what we choose here. I just want to see the predictions for this model. The predictions are a straight line. And as you can see, they are getting updated. The model is learning. It learned to flip them, but that's the best it can do. Okay, so you might say, well, the issue here was we only had 1 unit for each dense layer. So let's go ahead and increase these units. And now what happens? These units tell you the output feature space of each layer. So this dense, the output will now be 64 features, and the same for this dense. Let's go ahead and draw that out. This one's a little bit more complicated, actually. So we've got our 64 units now. Now, what happens with that? We take our input data, that gets multiplied by a weight, and that gives us 1 feature. We take our input data, that gets multiplied by another weight, and that gives us another feature of this dense layer. And we do that 64 times, so this layer has 64 weights. The next layer is a little bit more complicated because the input layer is 64 features, and this output is going to be 64 features. So what happens there is we take the first feature of the output of this dense, and that gets multiplied by 64 different weights, and they all get added together. And then we do that 64 times. So the parameters of this layer here is actually 64 times 64. And then for the final dense layer, since that has an output of 1, we just take these 64 features that are outputted here, multiply them by 64 weights, add them together. So this should have 64 weights as its parameters. Now, you're really going to have to trust me on this one, but if you do all the math and you factor out the inputs, you will end up with the exact same situation that we had before. It will just be a number times our input. You don't have to trust me. We can see what happens here. Let's build this model. And actually, let's go ahead and view the model summary. So we actually didn't view the model summary before, so let's actually go back one step. And so before I said we had three parameters, 3 weights. Each dense had 1 parameter, and that's reflected here. So now let's go to our 64 units. And as I mentioned, this one was going to have 64 parameters. This was going to be 64 times 64. Then this one was going to be 64. So now we have tons of weights. So we should be able to learn lots of different functions, or at least you would think. But I showed you, or I told you to trust me, that the math will actually work against us here. Looking at the predictions, again, we have a straight line, and you might notice that the model trained a lot faster than before. So again, we have a straight line. So what's happening? Why are we not learning this simple function? Well, we don't have any activations, which is what this warning message is telling us. So what do activations do? Well, let's just go ahead and add a couple here. The final activation needs to match our loss, and typically you do no activation for regression. So now let's go over here, compile, and now let's look at our predictions. Oh, just adding those activations has solved our problem. Now we are learning this quadratic function. So I'll just go ahead and stop training there. And what happened there? So we added a soft plus activation, which looks like this. So the magic is that these dense layers, they are applying a linear transformation. No matter how many units you use, it's always a linear transformation. The features are a linear contribution, a linear combination of the input features. What the activation does is you put it between the dense layers, and it applies this nonlinear activation. See, this is, as you can see, it's a nonlinear function here. So you do a combination of a linear transformation with the nonlinear activation, and now you have this powerful function. It's actually a function that can approximate any function in the world if you have enough data and enough dense layers and enough units, and you use your nonlinear activations. That's what makes neural nets really efficient, because all these computations, this linear combination and the activation, are both really easy for the GPU to compute. So then, if that's all neural nets are, then what's so complicated about deep learning? Well, you often don't have infinite data, and you can't just throw a giant model at your data. You have to choose the layers which best fit your data. So you might think, okay, how about I just choose the perfect model for our data? What's going to happen? What's going to happen there? So let's go back to our data, and let's make a very simple data set. Actually, I want to make the slope larger than 1. So what I'm going to do is I'm going to add some targets here, and then we're going to end up with a slope of 5 because we have 5 targets. As you can see, our slope is now 5, and we're going to submit that. We don't care about this. So now, as I said, we're going to make the perfect model. We know that our data, we know it's just y equals mx. And that's exactly what we have here, y equals mx. And so let's go ahead and run this model. What happens here? Well, we're expecting a slope of 10, so it's taking some time. Yeah, might be here a little while. It didn't get there within the epoch limit that we set. It got close. So what happened here? We made the perfect model. So neural nets are actually expecting to have a large number of parameters. So the optimizer is what updates the parameters. And if you have a single weight, then our model was effectively this weight times input. So when you have a single weight, you can only adjust so much to get to your final predictions. If you have a lot of weights, all these weights can get updated at the same time. And then that results in a very large change in your output. And we can see that if we just go back over here and we go back to our model and we just, we actually have to add one more dense because we have to match the target dimension. But now we'll see that this model will train much faster. Yeah, see, it hit a slope of 10 pretty much immediately. And yeah, so we can see how fast the loss hit 0. All those weights just immediately got updated and found the solution. So what we saw there then is neural nets are actually very inefficient. We knew the solution. We knew that the solution is y equals mx. But when we tried to train a model on that data, it took a very long time to update the weights. And it took a much more powerful model to get to the solution faster. And that's kind of the lesson with neural nets. When you know how the relation between your inputs and outputs, if you already know that there's a simple function or a simple model that can find that relationship, then neural nets are sort of overkill and not the best solution. But if you have a problem like image classification, it's not clear what function you could write to go from your input image to your classification label. And in those cases, then the neural nets, which are powerful but inefficient, they are our best solution that we have at the moment. And that's where they come into play. So today we just went over some simple layers, and I think in other videos we'll go into some other layers that we can play with. Thanks.